Hello, this is Integrated Math 3, and we're going to be looking at Module 4 review. This is the answers. So question number 1. I think whenever you go toe-to-toe with one of these rational expressions, what you should do is just factor. So that's what I did. I pulled out the 3, and then I factored the difference of two squares pattern. Now what this question is asking is, what's going on when x equals -1? So when you factor this, you see that these would cancel out. And that doesn't mean, that's not our whole necessarily, but down here for this one we see that the vertical asymptote is going to be at -1, so that's the answer for that one. Next one, I did the same thing, just factored the top, and then I factored the bottom. And then what is happening at x equals 2? X equals 2, well, there's this trick that you could do. I see that these look almost identical, but the x is negative, the x is positive, the 2 is positive, the 2 is negative, so these are opposites. So if I factored out a negative, I could make it look like the one that's in the denominator. So and then those would cancel out, and we see that since they cancel out, at x equals 2 would be a whole. Question number 3. We have the difference of two squares pattern on the top and the bottom, but I did the same trick where I pulled out a negative, and that would change that to be a -9, and then that would change that to be a positive x squared, which then I could just rearrange so that it looks exactly the same. So we see that when we factor the difference of two squares pattern, we have x minus 3 and x plus 3. Same thing on the top and the bottom, it's just that we have a negative on top. Okay, so what's happening at x equals 3? X equals 3 is this for this factor here, and that cancels out, so that's going to be a whole. Number 4, factoring, and then we're looking at when x is 1/2. So factoring up top, I see that this as a 0 would be 1/2. So this as a 0 is 1/2. So it's not on the denominator, so we're not going to have a whole or vertical asymptote, and since it's in the numerator, we're going to have an x-intercept at 1/2. Okay, question number 5. It says what's going on at -1. Now I went ahead and factored it, but then I didn't really see anything. And so then I went back and looked at standard form for the numerator and the denominator, and I see that if I take the y-intercept at the top and the y-intercept at the bottom, that would give me -1, so then we have a y-intercept. Okay, number 6, a little bit similar. I factored it. I didn't really see anything going on at -1, so then I looked at the degrees. The degrees are both the same, so that means that we're going to have a horizontal asymptote at the coefficients of the leading term, so that's 3 divided by -3. So that would be -1, so that's going to be a horizontal asymptote. Now number 7, since the bottom is bigger, I just knew right away that if the bottom is bigger, if it's going to be a proper fraction, then we're going to have a horizontal asymptote at y equals 0. And then also this is kind of a clue. See if it says y equals, that's either going to be a y-intercept or it could be a horizontal asymptote. So horizontal asymptote for that. For question number 8, it says find x-intercepts, vertical asymptotes, all the 8 characteristics. That's what I was just kind of looking for. So whenever you go toe-to-toe with one of these rational expressions or functions, what you guys should do is factor. So I factored the top, factors of 15 that give me -8 are -3 and -5. And then I factored the bottom, don't forget about the 2 in the front. And then after that, then we can kind of analyze and check it out. So I start off with the points of discontinuity, or the restrictions, which it can't be a +2 or a +5. And so since the 5 has a common factor on the top, that's going to be a whole, and then the vertical asymptote is going to be the 2. X-intercept is going to be at 3, and what we do is we just look at the numerator to find the x-intercept, the zeros of the numerator. Y-intercept is going to be the y-intercept at the top divided by the y-intercept at the bottom, so that's 15 over 20, which reduces to 3/4. Horizontal asymptote is going to be 1 over 2. The degrees are the same, and so we take the coefficient of the leading terms, 1 over 2, and then since there is a horizontal, there's no slant. Now question number 9 is a little bit tricky, and the reason why is because as we factor this, we see a couple things. We see that we have the same factor twice, and then also on the bottom. So when we're talking about our restrictions, we have -4 and -5, so we have to stop right there. We have to say, listen, -5 is a problem, right? It causes an error. So when these cancel out and we see that we have a whole at -5, does that mean that we have an x-intercept at -5 as well? So whenever we have an issue where it's like, hold on a second, is it an x-intercept or is it a whole or is it both or what the heck? The whole, the restriction, or whatever is going to be the excluded value, that's going to outweigh the x-intercepts or the y-intercepts. Okay, so there's no x-intercept for this one. All right, vertical asymptote is at -4. Horizontal asymptote is at 1 because the degrees are the same. Take the coefficients, and then no slant asymptote. Now for question number 10, it says write the function. These are kind of tricky, but basically vertical asymptote, there is none, so that means that there's not going to be anything left over in the denominator. The horizontal asymptote is there is none. And then, so we're kind of left with nothing at the top, these first two. And then it says that there's a hole at x equals -2, so that means that we have the similar factor on the top and the bottom. And in order for it to be -2, it would be x plus 2 on the top and the bottom. And then it says it has an x-intercept at 0. So the only factor that would show an x-intercept at 0 would just be x. And we can see that the top is bigger, so that makes it no horizontal asymptote. Instead, it's a slant. And then the vertical asymptote, there would be none, so it follows those criteria as well. Okay, question number 11, it says write the function that has the following. Excuse the smudge there. It says vertical asymptote at 2, so that means we're going to have a -2 in the denominator. Horizontal asymptote at 2. Okay, so that's going to be the coefficients. And so that means that we have the degree is going to be the same on the top and the bottom. And then it says a hole at 3, so +3 would fit right there. And then x-intercept at 3. So then we have, well, see, this is another scenario where we can't have a hole and an x-intercept at the same place. So I put the other factor up there, and maybe that's what it's referring to. All right, for questions number 12 through 15, what I did to solve these, it said just to match the graph to the function. So I just find like real key things about attributes of the graph. So look at where the vertical asymptote is, where is the horizontal asymptote, where is it crossing the x-axis. Okay, so this one right here, it's crossing at, looks like -2. So which one would have a x-intercept at -2? So it looks like that one. You know, and that's how, I mean, you guys don't have to necessarily do it that way. You could have looked at the vertical asymptotes and stuff just to figure it out. Notice that I labeled a couple of things as I went through. So just use the 8 characteristics to try to narrow that down. All right, so on this side, let's take a look. It says, what is a rational function? So just remember that it's a polynomial divided by another polynomial. So it could look like this, it could look like this. Now what is not a rational function? So anything that doesn't have a degree, a variable with a certain degree. So that means that, see, we have 2 to the power of x. That's an exponential. That's not considered a rational function because it's not a polynomial. So if you recall in the previous module, module 3, you had to figure out what a polynomial was. So just think it's a polynomial divided by another polynomial, okay? Which also means that it could be a constant function as well. All right, so when it comes to proper and improper fractions, just think it's the denominator is bigger than the numerator. What is the horizontal asymptote of a proper? So proper is when the denominator is bigger. So if the bottom is bigger, it's y equals 0. What are 2 ways that you can get improper rational functions? So if the degrees are the same, or if the bottom is bigger. Okay, I don't know what the hell. Oh, top is bigger, sorry. If the top is bigger. So here's an example of the same, and then here's an example of the top is bigger. Horizontal asymptote of an improper function whose numerator, so they're equal, the same. So if the degrees are the same, we take the coefficient. So if this was the scenario, it would be 3/4. So horizontal asymptote is y equals 3/4. What is the horizontal asymptote? Whose numerator degree? Okay, so the numerator is bigger than, so that means that there is going to be none because the top is bigger. It's going to be a slant asymptote or an oblique asymptote. What's the domain of any rational function? This is something that we've been drilling. It's going to be all real numbers such that, that's what that line means, and then whatever your excluded values were, whatever your restrictions were, whatever the points of discontinuity were, your PODs. So what is the range? Well, it depends on the horizontal asymptote mostly, and if we have parabolas, don't worry about this so much, at least with our test. How do you find the x-intercepts? It's the zeros or the solutions of the numerator that don't divide out. Refer to the backside of your stamp sheet for that. Horizontal of any rational. I'm not sure what that is asking. It says the degree of the numerator and the degree of the denominator. So if the bottom is bigger versus the same, that's how you can tell if it's going to be a horizontal asymptote. Okay, so bottom is bigger, it's y equals 0, and if they're the same, it's the coefficients. When do you have a hole? That's going to be a POD or a restriction that divides out. And then how do you find the y-intercept? That's going to be the y-intercept of the numerator divided by the y-intercept of the denominator. How would you add two rational functions? LCD, then add numerators. Subtracting is similar, so just be careful to distribute the negative. So like if you had an example like this, if you have a negative right here, we'd have to go -3 times x, -3 times -1. Multiplying two rational, we just first cross divide, so any common factors, divide them out, and then multiply horizontally across. And then I went ahead and scratched this out because I think we were referring to dividing. So if you're going to divide, it's similar to multiplying, where you just multiply by the reciprocal. That's what MBR stands for. And then when you're solving two rational functions, it's best to multiply both sides by whatever the LCD is. That eliminates the denominators and makes your life a lot easier. An odd function, it reflects over the origin. So whatever values, like let's say if you did f of 2, f of -2 would be the same value but the opposite. Okay, and then the even function, it reflects over the y. So if you put f of 2, let's say you did f of 2 and you got 3, f of -2 would also be 3. So think of like a parabola right on the y-axis. Okay, synthetic division is great, but when do you have to use long division? That's when you're dividing by a degree of 2 or more in the denominator. So when we don't have just like a x minus 1 in the denominator. All right, moving over here, we've got it looks like a rational function that it wants us to find a bunch of things. So we can tell that this is improper, and the reason why is because the top is bigger. X-intercepts, well, I factored it first. So up top, this is the difference of two squares, x minus 3, x plus 3. And then I factored out a 2, and I got a x minus 3. So we see that these two factors here can divide out. So that means that we're going to have a hole at x equals 3. And then we won't have any vertical asymptotes, and our domain is all real numbers such that x doesn't equal 3. And then I went ahead and I found the slant asymptote rather than the range. So in order to do that, and it's hard to see. I don't know if you guys could. Yeah, there it is. Okay. So I have to take what it's being divided by and divide it by here. So this one's kind of tricky because how do I go from a 2 to a 1? You have to multiply by 1/2. So 1/2 times 2 would give me 1. So just remember, you have to take the opposite once you put those down there. So anyways, this is my slant equation. And then end behavior is going to be the end behavior of my slant equation or my horizontal asymptote. Okay, so this one it says, this is just graphing it, okay? It's over 1. And then let's see, x-intercept, this is just a linear equation. There's no holes. Okay, we don't have any vertical asymptotes. The domain is all real numbers as opposed to having a restriction. It's a polynomial. And then it said graph both of these. So what I did here is I put both of them. This is f of x, this is g of x. And we can see that they intersect right here, except for one thing. That if you were to go back to f of x has a restriction at 3. In fact, it has a hole at 3. So as f of x is coming through right here, even though g of x is crossing that point right there, 3, 3, there's a hole. So technically the solution is that they're never equal. There is no point where they're equal. Okay, now the next one where it says when is f of x greater than g of x? So when is f of x above g of x? And so we could say any values over here, like if you chose 5 or 6 or 7 or whatever, so any values of x that are greater than 3. And then when is g of x bigger? Well, g of x is on top of f of x in this interval back here. So it's just any value of x that are less than 3. So if you chose 0 or -10, that would work. Okay. All right, so on this page, let's zoom in. We have question number 19. It says simplify the rational expressions or the following expressions and pay attention to operate. Okay. So here we want to, since the denominators are different, I went ahead and factored. So this is x minus 1 times x plus 1. So what this denominator is missing is the x plus 1, so just multiply it to the top as well. And so now we have 2 times the numerator, and then we have 3. We didn't have to change this one. So now what you do is you put it over the LCD and then distribute and combine like terms. And so that's the answer that I got for question number 21. Question number 20, same thing. Right now the 2 doesn't have a denominator other than 1. So we look at, okay, 1 and x. So this needs to be multiplied by x on the top and the bottom. So now we have 2x, and then this is what I was talking about before in the previous videos, that this negative here has to be distributed to both of these terms here. So negative, so you're basically saying subtract 3x, subtract 1. Okay, and then combine the like terms. This is what I got here. Question number 21. When you see something like this and it's multiplication, you want, look at my work over here. See how if we divide all this stuff out, it makes our life way easier. So before you start trying to multiply this, just factor it and see if anything divides out. So a common factor between x squared and 2x would be an x. Pulled that out. I factored this quadratic right here. This is the difference of 2 squares, so that's x minus 2, x plus 2, and then down here I can pull out an x squared. So x minus 2 cancels out, the x plus 2 and the x plus 2, and then the x plus 4s. And then we do have an x up here and an x right there, so this one's going to cancel with one of these down here, so I'm going to be left with 1x on the bottom and just a 1 on the top. Okay, so factor first, then divide out. Number 22 is division, so we're going to multiply by the reciprocal, but first I'm going to factor. So x minus 1, x plus 1, those can't really factor. And I'm going to multiply, I'm going to what am I trying to say? Swap, there it is, x plus 1 and the x times y. So x times y is up top in the numerator and the x plus 1 is down below. There's a common factor that can divide out, and then this x can cancel out with one of these, and this y can cancel out with one of those. So we don't have any x and y's up top, but we have an x minus 1, and then just the x and the y left below. All right, they're getting more challenging. Here is basically a proportion where this and these two denominators are the same, so that means that the numerators have to be the same. So really, we don't have to look at the denominator in this case, or you could just multiply both sides by the LCD, which is 4 for both of them. So those 4's cancel, those 4's cancel, and we're left with the numerator on this side and then the numerator on that side, and then just solve. Okay, and whenever we have a rational function like this, we want to double check the answer here. So x, yeah, that should be fine. Okay, 24. Equal sign, proportion. We could cross multiply, or let's see what I did here. Yeah, so on this guy, in order for, I factored this, so this is x times x plus 1, and this is x plus 1, so what this one is missing is an x, so I multiplied the top by it. So now the denominators are the same, and so I see that this is 1 times x equals 7, and so 7 equals x. All right, this one was a handful. This is called a complex fraction, and I mean, there's no getting around it. They are complex. So just a couple things. Let's look at it more easy. Okay, example. Let's say if I had 1/2 plus 3/4 divided by 2 over 3 plus 4 over 5. So the idea is this, is that what you first want to do is take these two fractions and combine them into a single fraction, or whatever. What is that going to be? So that's going to be a 2, that's a 5/4. So this would be 5/4. Okay, and then take these two fractions. I don't really care to do that. These fractions, and combine those, figure out whatever it is. I don't know if it's 2/3. I'm just going to write 2/3. Well, it can't be 2/3. Let's say 2/13. And then once you have it like this, then you're going to multiply by the reciprocal. So remember, this is division here. So you're going to multiply by the reciprocal, which this kind of just does a little backflip, where the 13's up top and the 2's down below. Okay, and then you could just cross divide and deal with it as if it was just a regular problem that you're more familiar with. Okay, so going back, let me show you what I did. Up top, this is x minus 3, x plus 3. So what this denominator is missing is an x plus 3, so I put that on the top and the bottom. So then the 4 stays there, but then I have 2 times x, which is 2x, and 2 times 3, which is 6. That's in the numerator. Combine the numerator, and so this is what's left over in the denominator, okay? And the numerator, right there. Now on the bottom here, this one is missing an x minus 3, this one is missing an x plus 3, multiply them to the top. And so that's going to be x minus 3, this one times 1 will just be x plus 3. So this is what it's looking like. Combine the like terms. And so now this is where we took these two fractions, combined them into one, took these two fractions, combined them into one. Okay? Now I'm going to multiply by the reciprocal. I'm going to keep this fraction exactly the same. Notice right here. Then I'm going to take what's in the denominator and flip it. Okay? Multiply by the reciprocal. So the 2x is in the denominator, and the x plus 3x minus 3 is right here. We see that these cancel out. So x minus 3 cancels out with that one, and the x plus 3 cancels out with this one. And we're left with 2x plus 10 over 2x. Now there is a common factor of 2 in these two terms, so I pulled that out. And then 2 times x, so this is multiplication, so those can simplify. And then you're left with x plus 5 divided by x. These two x's do not cancel because this is addition. That one was a tough one. All right, this one, we have to divide. So I'm using long division here. So notice how I approach this. We're looking at our first term, 2x. To get to 2x to the fourth, we'd have to multiply by x cubed. Take that, multiply it times the 2x to get this guy, and then multiply it times the negative 3 to get this one. Now notice how I took the opposite of both those terms, and then figure out what the difference is there. So negative 6x cubed. How do I get from 2x to negative 6x cubed? I'm going to multiply by a negative 3. Negative 3 times 2 would give me the negative 6. That's what I put down here. And then negative 3 times negative 3 would give me a positive 9. I took the opposite. It's just these things, they're not complicated. It's just that they just take a while, man. And you got to be super organized. You got to make sure that you put the right signs. So anyways, I get 12x. This to get to 12 would be a 6. Multiply both of them by 6. That's what I get. Go all the way down and we see that we end up getting a remainder of 0. So what you guys should do is, now that you've seen this, try it yourself and see if you end up with the same answer. Question number 27. This isn't factorable up at the top. Okay, I tried to maybe think that, see up here, you can't do that, but I thought maybe we could factor by grouping. So we're going to have to use long division. And so for question number 27, I put it right here. From x squared to 2x cubed, it would have to be a 2 and an x. And then multiply times all of those things. Now notice that we actually get a remainder here of 11x minus 7. So that goes up top, all right? And then we put our dividend in the bottom here. So whatever we ended up dividing by, that's what goes right there. Okay, so the whole purpose of practicing this long division is so that we can find our slant asymptote. Now remember, our slant asymptote is the linear equation, not the remainder. So we would just throw on a y equals, and this would be our slant equation if this was a test question asking for the slant. Okay? So that means that our end behavior, since our slope is positive, it's going to be like this. So as we approach positive infinity, it's going towards positive infinity, and as we approach negative infinity, it's going down towards negative infinity. Just keep that in mind. Okay, last one here. Factor the top, the bottom. Those two factors, they cancel out or divide out, and so we're left with x minus 2. All right, so this part down here, it says tell whether they're odd, even, or neither. We did something like this just to remind you that if we had f of a, if it's even, then the opposite. So this is what I mean. So see, like this example. So if we did f of, say, 2, it was right here, then f of negative 2 should be right there as well. So see how the y values are both going to be the same. Now if it's odd, on the other side, it's going to be on the opposite. So watch this one. So if we did like f of 3 and it was up here as a positive number, f of negative 3 would be the opposite of whatever that number was, which will make it down here. Okay, so that's what I'm looking at when I'm going through. So this one is even, I can tell because I'm looking at 1, I got 5. At negative 1, I got positive 5 as well. So I got the same thing on either side of the y-axis. This one is a neither because as I go through and I did 1, I got 4. Negative 1, I got 10. So it's not the same nor opposite. And then I did another example for 2. 2 and negative 2 don't get the same thing. Okay, I already told you why this one's even. This one's odd because as I'm going this way, it's going up. As I'm going this way, it's going down. And then this is going to be this, I already know this is a one of those touchdown ones. Okay. And it only is shifted down 3. This is an odd function, so I know that it'll be odd. odd exponent, which means it's going to be an odd function. And then this one, looking at the t-table, we see that at -1 it's -5, and then at +1 it's +5. So when the x values are opposites, the y values are also opposites. So that means that this is odd. This one is a neither. I showed the graph, and I can't erase it somehow. Can't make it smaller or whatever. Okay. This is what a radical function looks like. And then this right here, this is all I did was just use the polynomial technique where I labeled the zeros, and then I just did the disco method. Okay. So, anyways, that's what that is. Let's move on to the backside. All right, last page here. I just want to start by saying, man, as you guys do these graphs, and whenever you're practicing, you should always check with Desmos. So let's see. We need to find all this information here. So what I'm first going to do is just factor it. That's the difference of two squares. Down here I could pull out a 2. All right, so it says proper, improper. Well, we see that the top is bigger, so it's going to be improper. These things divide out right here. So that means that we'll have a whole at -3. Vertical asymptote, we won't have any because it divides out. And then we have an x-intercept at the remaining 0, which would be at +3. Y-intercept is going to be the y-intercept of these two, so -9/6. Right there. Yeah, I don't know why I'm looking over there. And then let's see, domain is going to be all real numbers such that it's not your POD. And then instead of your range, I found the slant asymptote. So we have to take this and divide it into that. So when you divide these two things cancel out, and I'm left with x minus 3 divided by 2. If I have x minus 3 divided by 2, that means that this is 1/2, or 1/2. And then this is -3/2, which is -3/2. So this is my slant equation. Okay, so we did the division. Sure, you can factor. You don't always have to use synthetic division or long division. Anyways, there's my slant equation, and my end behavior follows the end behavior of my slant equation. So let's look at it, what it looks like on the graph. Notice that I also placed my hole. It's just a line. Okay, when you simplify it, it's just a line. Okay, the actual problem. Just make sure that you put the hole at -3. Okay. Number 17, you're definitely going to have to use Desmos for this one. So this, I pulled out an x, and I was left with x squared minus 1. So factor that out. And then the x's cancel out, so that means that we're going to have a hole at 0. So that's where the hole is, right there at 0. And then it's a proper because the bottom is bigger. Since it's a proper, that means that I'm going to have a horizontal asymptote at 0. And then these two guys, these factors, that's going to be my my vertical asymptotes, one at +1, one at -1. And then what I had to do here, after I found all this stuff, I had to substitute in the value. So I substituted in +2 to get 1, and I substituted in -2, and I also got 1. So I plotted 2 points, so I know that this one went right here and this one went right here. And then in order to find these, you would just substitute a different value, like you'd have to go 1/2. Okay, I don't think you're gonna have anything too crazy like this on your test, so don't go crazy and freak out. But notice that my end behavior is approaching our horizontal asymptote, which is at 0. So as it's coming down here, it's approaching 0, and as it's going this way, it's approaching 0. So really, if you know your horizontal asymptote, you're going to know your end behavior, or where it's approaching. All right, next we have this one. So that I factored the top, pulled out an x, and then I see that these two factors cancel out, so that means I'm going to have a hole at 2. And then it's an improper because the top is bigger. Vertical asymptote, there is none. Notice that this just simplifies to x, which we're familiar with, y equals x. So y equals x is a line that goes like this. And so we see x-intercept at 0 and y-intercept at the same location. Domain is all real numbers such that it doesn't equal 2. And then my end behavior is the end behavior of the slant asymptote, which is right here. Okay, notice that it's basically just right in the line. All right, well, good luck. Study up. Look at your packets. Look at your reviews. Remember everything that I have ever told you, and I'm sure you'll be fine. Good luck.